Hi, welcome to the part 2 of the series. In the first part, we saw that RAG is not only about retrieval, augmentation, and generation. There are multiple layers, multiple steps which contributes to a effective RAG system. So in this video, out of all these steps and layers, we will be focusing on the very first layer, that is called data indexing. So in this part, we will be discussing especially only this step. So within this data and indexing step, what all we do is we have several data sources. We will discuss about how to make your data more structured and clean, so your RAG pipeline produces more accurate results. We will see chunking strategies, embedding models, which one to choose when, what are the properties of different embedding models. We will see the various vector stores and some indexing parameters. So without discussing more on this diagram, let us jump into the code. Okay, so for the sake of explaining the theory along with the code samples, I have structured a Jupyter notebook here. We will go step by step, whatever we have seen in the diagram. All these topics, this data source, chunking strategy, embedding models, and vector stores, and various embedding parameters, what are their importance. We will see all of them in action, how to implement them, what is the significance, what is the theory and the concept behind. So let us start one by one. The first topic in the diagram we saw is data quality, which is actually the foundation of the RAG system. So everyone have different types of data sources. It could be logs coming from applications or user activity logs, for example. Your API generates several logs, your server system logs. You can be having PDFs for documentation, user manuals like things. Document stores, for example, if you are using some tools like Confluence or some other documentation tools, wikis within the company, such documentation tools are also considered to be your data source. Along with them, you can have tools, for example, your ticketing tool, where you have customer support data and tickets, if you want to develop some AI or RAG system on the top of it. And also the actual databases, including whatever SQL, NoSQL, or any kind of database. So there is a huge variety of types of data each user can have. But at the end, the main thing, the most important thing is we should have a quality data. So why data quality matters actually? No matter how sophisticated your RAG pipeline is, and it also doesn't matter how advanced LLM you are actually integrating into your AI app. If you are supplying in the garbage, you will receive the similar results as an output of your RAG pipeline. So it is really important to clean your data, to structure your data in a way that RAG pipeline can produce better results, more accurate results. So what kind of data cleaning or structuring you can have? In general, in real world, you have noisy data. For example, your data might be having some unwanted HTML tags and formatting artifacts. When you supply such a data to your RAG pipeline, you can end up building wrong chunks. And your RAG pipeline, the retrieval stage in your RAG pipeline, retrieves wrong data, and at the end you end up receiving inaccurate results. Another example could be, generally people have inconsistent formatting. For example, as I have written it here, the date format. The more such kind of consistency you are having in your data, you are at a better position for a RAG pipeline to start building up. Encoding errors. The same text can be represented differently if you are using different text encoding. The example is in front of you. Don't in some other encoding may look like this. That looks really weird. So here the semantic meaning is totally lost from having such representation of the text because of you haven't used the correct encoding. Similar, the next point would be you might be having duplicate content. So that's pretty obvious. Also, sometimes you have some errors during OCR, that is optical character recognition. If you have a look at this, here on the top of I am having two dots. This might really cause a problem for RAG system, for a retrieval. and here we don't have it. Similarly, optical character recognition errors may occur if a 0 is misunderstood as capital O or capital I is misunderstood as small l. So such things should also be cleaned or at least clarified. So how do we do it? I'm not speaking about manually doing everything. There are tools for everything. So why data quality matters? We recognize the wrong patterns or noises in your data which might be available. But there can be more points. But I have summarized 2-3 main points, key data quality principles, which you should really consider before jumping into implementing a RAG pipeline. So strip out unnecessary HTML tags and special characters, remove duplicate content. Maybe this might be done manually, or you can take help of any LLM tool which can summarize and remove the duplicacy. Clean up OCRs. As I said, 0 O should be differentiated, 1 and this is small l, and RN, you see this looks pretty much like M. So how to fix OCR errors? There are tools to do that. For example, text blob and spell checker. You can check it out. I do not have any code samples for this part of this video because this is really user specific. You can have, maybe you are already having very clean data. If you are not having, you might be having some different type of data stored at somewhere. So I'm just pointing out the key principles which you should follow and the possible solutions you can think of. So this is about OCR and removing noise. And here the second principle is ensuring consistency. The date format, how the units are written, like kg and kilograms, dates units. Spellings, again you can use the same tools, text blob and this spell checker for fixing the spelling and grammatical errors in your text. And then there is normalization. I just briefly was speaking about this encoding stuff, how drastic it could turn your text into, that is unrecognizable if you do not use the correct encoding. So how do you fix it? So to fix it, you can just use the UTF-8 encoding throughout your text, if the data is in textual format, of course. So there is another example of using a different encoding. For example, cafe in Latin 1 is written like this, but in UTF-8 you will be reading the same text as this thing, but nothing means or translates to actual cafe. So this is best practice to spend some time, and regardless whatever is the original encoding there, you choose something uniform. For example, UTF-8 is quite a nice encoding and everything is easy to understand for you and for your RAG system. So again, there are tools to fix your encoding as well. They are written, you can explore them. And again, the last principle is the structure, the hierarchy. Generally, documentations having a tree-like structure. There is a heading, then there are subheadings. You might be having tables, then you might be having a list of pointers. So if such a structure is maintained, that is human readable, easily human readable, and as well as can be read easily by a program. So preserve structure. So following these all data cleaning principle, if you spend 1 hour of data cleaning, it can really prevent multiple hours of troubleshooting why your RAG system is not responding or not producing accurate results, and it really pays off. So next we are going to discuss more in-depth technical stuff where the implementation and coding stuff comes in. The first one is chunking. Chunking is literally like breaking your text into multiple pieces. Now, how big that piece will look like, what is the overlap that we are going to see. To create chunking, I am using Python packages from LangChain. And there are various classes, modules which can provide the chunking methodologies, but I am discussing here only those three. Recursive character text splitter, character text splitter, and NTLK text splitter. So these all three are available if you have installed the LangChain Python packages. So I'll make this project notebook along with the requirements.txt open source. There you can see which all dependencies you need to run this notebook. So let us discuss this first, recursive character text splitter. This is the most recommended splitter. You can use it in every case. Let us see how it is implemented here. So these are some log messages. If I directly jump into the constructor, how it looks. So here is the constructor, how to construct the object of recursive character text splitter. The chunk size. Chunk size is literally the count of the characters, nothing else. And we have this test overlap. Overlap is very important, and this overlap we will see in the splitters we are going to discuss next. Overlap is really important because suppose you are having a manual or user guide where a section which you are currently reading or referring to is dependent on the previous section. So you need an overlap. For a specific user query, what are you going to return? The piece of the code, the piece of the text which is most relevant, or also the piece of the text which is related to this. So when you make an overlap, it means the chunk size would be 100 characters, and from here the 20 characters will participate in the next chunk as well. So they have a kind of intersection. Two chunks have the overlapping knowledge. So when a user query comes in and your retrieval system works, then retrieval system returns you with two chunks which have this common part, these 20 common characters, and then you can build better context and the retrieval is better, or the response is more complete, for example. So back to the topic, the recursive character text splitter. The chunk size 100, for example, we have considered it here. Then text overlap is 20. Length function. So basically how to calculate a length. So this is the standard length function. This is not so important to discuss here. The important is the separator. So what it does, so whenever you pass in some text to this recursive splitter to split, it doesn't really care about the chunk size at first. These separators are always in the priority. Means even after 10 characters, if you encounter 2 new lines, then it will break and split your first chunk at those 10 characters. We will try to run this and we will have a demo. So before we jump into the demo, let me clarify a few more properties of this kind of splitter. Tries to split at the most meaningful separator first. That's why I shown you the definition of the declaration of our constructor here. So separators are prioritized. Paragraph, 2 new lines, new line, then sentence if there is a dot or full stop, and then you are noticing the space as well here. So this is indicating the sentence is ending. So this will always follow this in priority from left to right. This is the priority and this is the least priority. Then spaces and then characters. So if nothing is found, then there will be hard stop at 100 character or whatever the chunk size is. And if any one of them is found, the chunk will be created, can be created earlier than the chunk size as well. Works down the list of separator, always ensure the chunk does not exceed chunk size. So it never exceeds the chunk size. If a clean boundary like paragraph or sentence would make chunk too big, it tries to the next separator. So for example, if a paragraph or any new line is happening, for example, in 120th character, so it will jump on the next thing. Where is the dot? So remaining within the chunk size, it tries to find all those separator and creates chunks. So as simple as that. So let us try to run this thing. For this I have created a sample text. This is a sample text data for chunking strategy demonstration, and what it contains is some corporate remote work policy. So I have generated it using AI, nothing so fancy about it, but you have some topics, you have some paragraphs, you have some sentences here. So let us try to run this cell, and this is all about this recursive character split, recursive character text splitter, and this you just pass in the sample text and you split it, you get the chunks. Now let us see how the chunks look like. So in the beginning I have some logs, more or less like documentation. So these are the first 4 chunks which it has created. Chunk size was 100, but you see my first chunk is of 18 characters. Why? Let us have a look into the text. Because it got one new line here, one new line here, it considered it to be a new paragraph, so it did a split here, and you have a first chunk of size only 18, even though the chunk size was 100. Similarly, you go to the next chunk. This is saying like topic. Again, why it is only 32 characters? Because here you encountered a new line. Chunk 3 is of 95 characters. But please note that in chunk 4 you are having a overlap or other remote. These 3 words are, to be specific, these 20 characters, because the overlapping size is this one, 20 characters. So these are overlapped, but they didn't overlap. So you would have noticed that there is an overlap between chunk 3 and 4, but not between chunk 1 and 2. It has cut on the separator very strictly. So it's a special behavior of this recursive character text splitter that it prioritizes the highest priority separators over the overlap, so you don't see it. And how it is behaving is, recursive character text splitter found that this is really a heading of your text, and this is not semantically similar to your next line. That's why it didn't created an overlap between these two things. But in further chunks you can clearly see that it is happening. So that there is some intelligence behind the scenes. So this was our first splitter. Let us move to the next one. The next one is character text splitter, and again I will show you the constructor, how to build it. Character text splitter, this is fairly simpler than our previous one. This takes only one separator, and what it does with that is, here boundary logic for character text splitter is like, it splits only at the specified separator, builds chunk by adding text segment until the next separator would exceed the chunk size. So it also doesn't increases the chunk size, it just finds this separator and creates a chunk. But there is a caveat, it can still produce the bigger chunks. And when it will be happening? If you are having a single word that is long enough to surpass the chunk size. For example, in this case, if you have a single word which is of size 120, normally you don't see such big words, but for example, if you are having a URL like this, then what it will do? It will show the flexibility and it will create the chunk, the first chunk, which is actually bigger than your chunk size. So that's the only exception where it can create the bigger chunk than the chunk size. But that was not an exception here. The previous splitter strictly follows the rule that it never exceeds the chunk size. So let us try to run the second splitter. Here is the result, created 28 chunks. Here is the chunk number 1 of 99 characters. So it is different than the previous one. It only follows the separator to be the space as defined here and the chunk size. So it went up to 99 characters and found a space and did a split. Now here you see the more overlapping, because now it is already into a paragraph inside the text of a paragraph. So you can see the overlapping. This word is overlapped here. So this is how this character text splitter works, and I think I should be having that example here as well printed. When the text size or word size is way bigger than your chunk size. So here's the example. Let me go back to the code as well. So this was your normal example of the character text splitter, and here you see the next example where your text is, earlier I was using this text, but here I have created this, let us say, text to demonstrate where your chunk size can be bigger. So you see the separator is still the space. It will still make chunks based on this single space, but within this single word it didn't find any separator at all. So how did it split? H case demo text with 120 character word. So first chunk was normal text here, then the second chunk was 130 characters actually, and the chunk 3 was a normal. So here the normal text, then after space it found a really big word which it created a chunk with, which exceeded the chunk limit, and at the end you saw this text as a chunk. So this was our number 2 splitter, character text splitter, and let us move to the third splitter. So this is called NTLK text splitter. So NTLK by itself in its original form, I think it's called Natural Language Toolkit. They have their standard package available as well, and this is the LangChain wrapper around that official package. But what is NTLK and NTLK text splitter? They do the same job. They are the splitter which splits the text by sentences, as simple as that, and remaining things are like it obeys the chunk size boundary, splits at sentence boundaries using NTLK's sentence tokenizer. So you really need not to give any kind of separator here. You observe, you can see the constructor here, I haven't given any kind of separator. So it is specially built for this sentence, and the intelligence is already inside the package. So it splits at sentence boundaries using NTLK's sentence tokenizer. If you have a look at the constructor, I haven't given any kind of separator here. So it has got its intelligence how to make chunks based on sentences. It may be dot, it may be a new paragraph, it may be a new line, whatever. We don't really need to worry about it. It merges sentences into a chunk until adding another would exceed chunk size. So it will make a sentence and chunk size is 100. You have occupied only, let us say, 40 characters. There is still space. It will check what is the next sentence length. If it fits within the overall chunk size, that is 100, it will add it to the chunk, otherwise it will not. But what will happen if your sentence is really long and it cannot be accommodated in the chunk size you have declared? In that case, it will create a single chunk of a bigger size than the chunk size. So the chunk size is a soft limit. It will not break up sentences to enforce the limit. So as I shown you, this is a very simple splitter with a simple signature and the declaration of the constructor. And if we try to run, by the way, these logs are coming from the library itself, but we need to focus on this. So first sentence, the heading, subheading, then this is the next sentence, then this is the next sentence, character 2. You observe this is already 191 character long, so it has exceeded the chunk size. And why? because this is a single sentence, there are commas, not dots. So it was essentially not obeying the chunk size, because it couldn't fit it into a single chunk. Okay, again, do you notice that there is no overlap? The first chunk and second chunk might be clear to you, as I explained it in the previous splitters case, but here this is already into the paragraph. I still don't see any kind of overlapping at all. So the reason being, this is essentially a sentence splitter. It won't break that protocol by itself. What I mean is, the overlapping size here we have declared to be 20. So what it has tried already, using this overlapping size of 20, it is searching that if there is a sentence of size 20 characters in your previous chunk. It didn't find any. That's why you don't see the overlapping. So it will overlap not by characters but by sentences of that overlap size. So that's a basic rule. So here I have explained the three very basic splitters. Let us move to the next one. So we are still discussing chunking. So chunking, we have seen the three different types of splitters, but there can be different approaches to chunking. So far what we have done as a part of chunking is by splitting the text more or less in a hard way. Okay, there is some intelligence inside those splitters, for example sentence base, and respecting the separators priority. But the more effective chunking is like semantic or topic based chunking. So what your RAG system or RAG pipeline is supposed to do, it is supposed to respond you with some user query. And what if you have created the chunks which are related? So in this semantic or topic based chunking, we won't be using any kind of separators, no overlapping size, no fixed chunk size. But what we can decide is, we will read the document line by line, and the moment we see that topic is being changed, the next line is speaking about something else, we will chunk it out, so that you have really clean chunks already prepared. And imagine how easy it would be for any system to retrieve the related information to a user query. So there is no fixed class or module to achieve such a chunking. You will have to define your own strategy. For example, we will be splitting, in this example, we will be splitting text into sentences, and we will calculate the semantic similarity between consecutive sentences using TF-IDF. What is TF-IDF vectors? That we won't go in details in this video. Just to mention it briefly, it is called term frequency, inverse document frequency. It is a numerical static used in information retrieval. So we won't really go into the depth of this TF-IDF, but what we are going to do is, we are calculating a score, how similar a line is to its previous line. Create chunk boundaries where the similarity drops. Then we will define a threshold. For example, we are creating a score. This line is that much similar. The next line is that much similar to its previous one. Then we will create the chunks using let us say from a threshold. We will chunk it out. So that way we will be implementing our strategy. And you can certainly define your own as well. This is just an example. So this is a function which will do the chunk by semantic similarity. And what we are going to do is, so here we are using the NTLK official package, which I was speaking about. We used earlier the wrapper from the LangChain of NTLK, but here it's the original one. So we are essentially splitting it by sentences. As you already know, NTLK is expert in making chunks based on sentences. So we have sentences. Next, what we do is convert sentence into numerical vector using TF-IDF. So we have a vector. It's not a vector store like we do have ChromaDB or Fez, but this is something different. So in the next step, what we are going to do is we are going to create vectors out of these sentences. So by vector, we are not yet created, we haven't yet created the chroma or phase like vector stores, but just focus on this approach, that is semantic and topic based chunking. So we have created vectors using TF-ID vectorizer. Step 3 will calculate the similarity between consecutive sentences. So this is a critical step. So how I and I plus 1 sentences are similar, there will be some floating value. So how it does it? Similarities contain the cosine similarity. So this will be an array of some floating numbers between, let us say, -1 to 1, and what it will have, the cosine value of the angle. If you would have learned in trigonometry, if you have the angle 90, what is the value of cosine of 90? That is 0, and cosine 0 means 1. So the angle between two pieces of text decides how similar they are. If the angle between two texts in a multidimensional space is 0, it will give you number 1, which means they are almost same numbers, and hence the same text, because vectors are the numerical representation of your text. So here it will be a list. Let me run it in a debug mode so that you can always visualize. So let us examine. So it created 10 chunks here using this tokenizer. Ten chunks out of the text we had already, and then it created vectors out of these sentences, means numerical representation. Now it has created this list. What a floating value at 0th index tells you, it gives you a similarity score between this and its next sentence. So how similar are two consecutive sentences, that is maintained in this scorecard. Now what you need to do is, based on some threshold, for example, within this you can decide if a similarity between two consecutive sentences goes beyond a certain limit, you are going to break and make a new chunk. One chunk we have already created, one kind of chunking we already done. We are doing a kind of re-chunking based on similarity. So this logic is doing all that using the chunk boundary. So that is being supplied as a input into the function, and the default value is 0.5. Okay, this is coming 0.1 at this moment. So 0.1 is the boundary. So wherever it finds the similarity score is going below 0.1, it will create a new chunk. So it is a two-step chunking procedure, but very, very effective when it comes to producing more accurate results out of a RAG system. So let me run this and let's have a look into the chunks. So chunk 1 is like this thing, 352 character irrespective, because now you do not have the chunk limits, but what decides the chunk size is the similarity and the similarity threshold what you have defined. So lower the similarity threshold you are passing in the function when calling. We saw I was passing 0.1. If it would be 0.5, then you will be having smaller chunks, because then the algorithm expects more similar sentences to be kept in a single chunk. So this is how this kind of chunking you can consider while implementing in your RAG pipeline, to be specific, while data indexing. One more kind of chunking is important to know, that is token based chunking. So token, you would have heard about token if you are into the AI field and you use various LLMs. So LLM unit of counting a text is token, and a token is essentially not a word. So let us go through the text what is written here. Token based chunking splits text into chunks based on the number of tokens, not characters. Earlier the chunk size was representing characters only, but now it's token. This is especially important for LLMs, as most models have token limits and count token differently than characters or words. So what are tokens? Tokens are not always words. They can be word pieces or punctuations. And this really depends LLM to LLM. For example, cat is equal to one token. For we are speaking here about the OpenAI. And unbelievable, this is word unbelievable, unbelieve and able. It contributes to be 3 tokens. Similarly, hello world, it has considered only comma, 1 character to be a token as well. So this depends totally upon which model you are using, what kind of tokenizer that LLM is using to calculate the number of tokens. So why it is important? So this is important while calculating how much text or number of tokens you can send in one request to your LLM. And what is the context window size, the short-term memory, the text which LLM considers while responding. So that's also calculated in terms of tokens, not words, not characters. So a token is a unit of text as defined by tokenizer, a word, part of word or punctuation. And this is very, very much LLM specific. This unbelievable, for example, might be 1 token for another LLM. So you cannot predict it in advance, or similar implementation won't work for every other LLM. Token-based chunking ensures each chunk fits within the model context window. So model context window is fixed. There is a limit applied by every other LLM. And how are you going to fit that context window? Using tokens. So you should really have chunking based on tokens if you really want to achieve this. Common tokenizer, for example, tick token is one of the tokenizer which is being used by GPT. For example, such calculations, 3 tokens, and hello world have 4 tokens. And below is a demonstration finally to see how we can actually implement token based chunking. Again, there is this class called token text splitter which you can use to create tokens as chunks. So if I go into the constructor, again overlapping and chunk size you can do. So chunk size, so this is not characters. This says I'm going to embed 100 tokens into single chunk, and 20 overlapping, they are not characters, they are 20 overlapping tokens. As simple as that. And here is the model name. So as I said, this is very specific to each LLM. What is going to be a size of a single token? This is the 100 chunk size, means 100 tokens would be there, but what would be the size of each token? That will be considered by this model name which we have provided right here. So use 3.5 turbo tokenizer which is in the background using tick token. OpenAI's official fast tokenizer library it is. And when you installed LangChain text splitter, it automatically installed. So all the dependencies to run this notebook are here. So as soon as you install this dependency, the tick token is already installed in the background and it is doing its job when we run this thing. So nothing else, some print statements, and I can run it and we can see the output. So here we see how the chunks has been created. So the token chunk 1, we have here token count. So this is some metadata information. It's not yet the chunk. So in the content preview, you will see the actual chunk that has been created, and it is essentially either 100 or less than 100 of token size. Yeah. So it is not printing full characters. Otherwise, you could have seen the overlapping stuff between chunks. So overlapping, it will be doing by overlapping tokens, not the characters. So overlapping size was 20. Here the size again essentially means tokens, not the characters or the words. So far we have seen several kind of Splitters. Earlier we see some character splitters and lang chains and TLK splitter. Then we saw the different chunking strategies, for example token based or topic based chunking. Now chunks has been created. We need to store them in actual vector database. So now let's take the semantic chunks and store them in vector store with embeddings. So I'm not going to store all the chunks created by every other splitter or every other strategy. I am just going to take the semantic chunks, means topic based chunks we created. You remember where we created a scorecard, how similar a sentence is to its next one. So on the basis of that, I'm using that function to create chunks, and we are going to actually save those chunks into a vector database. Let us see how to do it. So this is our cell, and we are going to use ChromaDB. By the way, there are multiple implementations, multiple types of databases which you can use to create your vector store. ChromaDB is in-memory vector store, and that is very good for such small demos. And I will show you what are the properties and the difference between using different kind of vector stores. So let us go. Here are some print statements. So this is the function chunk by semantic similarity. So these are the chunks. This we have already discussed. Now you have the chunks. So what is the next step? In fact, the first step, that is initializing the embedding model. So what is embedding? So far we have chunks. They are no more than a piece of text. But now to make a vector store, a store of vectors, we need an embedding process. What is embedding process? Embedding is called creating a numerical representation of a text. So that is what we are going to do. And who does it? There are embedding models which we will feed. Okay, this is my text or chunk. Now create an embedding. Now create a vector for it, and I am going to store it in a vector store. The one thing that is very important to consider while choosing an embedding model, that is the importance of dimensions. We are quite used to see until 3-dimension stuff, X, Y, and Z. But as I said, most of the time the similarity is considered by the distance in a multi-dimensional space. For example, if we speak about cosine similarity, by the way, there are different kind of similarities which we will see briefly in a minute. So similarity, how we calculate similarity in 2D, an angle between two lines, and you calculate the cosine value of that angle. Higher the value of cosine, the higher is the possibility that those two texts are similar, or those two lines are closer to each other. Now you can add more dimensions to it to consider various aspects, because text is not as simple as your single line where you can calculate the angle between them. So you will be surprised how many dimensions an embedding model can embed into a vector. The model which we are going to use in our demonstration can produce up to 384 dimensions. 384, and we are in day-to-day life are used to experience only 3 dimensions. So that's why we need embedding models to create vectors out of a text. And here I have listed multiple models and the dimensions they can create in a vector. For example, these are OpenAI model, 3072 dimensions. It is of course high quality and for sure expensive as well. But implementing it is really easy. You need a sentence transformer like class or any other library you can use, which can create an embedding object or embedding model object here like this. And what you need to do? Simple. You have a tool which can do embedding, which can create vectors out of what? Out of your chunks. You just pass in your chunks. That's it. And now you have embeddings. Next, what you are going to do, you are going to save them. Make a client of our vector store here. This is our client. Now you create a collection object, and then in the collection you keep on adding your all the chunks. That's how easy it is to create 384 dimension vector in a few seconds. But here is an important thing which I would like to mention is, while creating this collection object, there are different kind of similarities. Means on what kind of similarity tool you are creating your vector store, or how to determine two texts are similar or not. So there are different kind of similarities as well. For example, cosine similarity. So this is simply an angle between vectors, but always remember it's not a two-dimension thing we are speaking about. 0 degree is not meaning that there is a 0 degree angle between two lines. It's 300 and something, I forgot the number again, 384 dimensions where we will calculating, where this tool is calculating the angle while retrieving the text. So the value might be -1 to 1. So the bigger the angle, 180 means they are totally opposite. So bigger the angle is, cosine value is lesser. So lesser means they are not the same. In fact, the opposite text semantically. So 0 angle means cosine value will be 1. So the 1 is higher value. So it means they are very likely to be exactly similar text. So that's how the cosine similarity works. And there are Euclidean distance as well, another type of similarity mechanism. It simply works between the distance. So 2 points, and you need to calculate the distance between those 2 points. That's why it is called L2 as well. So it measures a straight line distance in n-dimensional space. So how it does, we are not going to discuss it in detail, but that's another kind of similarity mechanism. And there is inner product, which simply is a combination of both of them. Best for production system with normalized embedding, and it does. So here it is, measures both angle and magnitude. So magnitude is like the length of your text. For example, a bigger text might also be semantically similar to a few words. In cosine similarity, it doesn't consider the magnitude. Means a 10-word sentence, I'm having a sentence one of 10 words, another sentence of 4 words. They might be semantically exactly similar. Means angle between them might be 0. So cosine similarity focuses on the semantic similarity and angle, not on the magnitude. Means how long your lines are before calculating the theta, the angle between them. Cosine doesn't value that, but L2 does that. And this inner product considers both kind of similarities. And why it is important? Because we pass it in this property. So the collection, the embedding, the vector store we are going to build will support cosine similarity. And this is quite majorly used kind of similarity while implementing such retrieval systems. So you can easily choose cosine similarity without any problem. There are consideration when to do what. I have texted it here. If you want, you can read it later. And where it will be created, it will be lying in this object in memory. So you just need to run it, and 380 whatever it was dimensional vector store has been created in seconds. Embedding dimension 384, we have used this model, and yes. So we have created chunks, we have stored chunks into the vector store. So the next step is how we can query vector store. Means we have a user query, and how do we get data out of it. So there are two approaches which we are going to discuss. One is very popular and largely deployed and used by developers. That is just shooting your query directly into the vector store. Another is hybrid search. It really improves the results, the accuracy which you are going out of the vector store. So let us see the APIs, how you can implement it. So we will be querying the collection object, the in-memory ChromaDB vector store, which we created in the previous cell execution. So if we have executed it, it will remain in the memory in Jupyter Notebook. So we are going to query. We are passing in two parameters. One is the query embeddings and the result. So this result is like it will search and it will give you three best matching results from the vector store according to your query. Now what is this query embedding? If you remember, we stored in vector store the numerical representation of our whole knowledge base or text or whatever it was. We chunked it, we created chunks, and we converted it into the numerical representation and we stored it. Now if we want to retrieve something, we will have to convert our query also in the same way. We will have to create vectors or embeddings out of our user query as well. That's why it is done here. So we have the embedding model, the very similar with which the chunks has been stored in the vector store. So we are using the same model here and we are creating embedding, and this query embedding, this is actually the numerical representation of user query, and we are passing it into the collection to get the result. And that's what we are going to do. Rest of the things are just printing what is the response, what are the other properties received in the response, which are important to consider. If I try to run this, so query was what are the internet speed requirement for remote work. Now query has been converted again to 384 dimensional vector, and now we are implementing simple vector search. Top 3 results has been returned. Have a look at the score. So this is the cosine value of the angle. This is the highest, so it has put this content at the top, rank 2 and rank 3. So that is how simply you can implement your vector search. Hope you find the video informative. Thanks for watching.